let's summarize the mathematical model before we look at how to solve it numerically using the finite element method. Our mathematical model consists of governing equation and boundary conditions. We'll take a look at the governing equation first, and then we'll take a look at the boundary conditions. The governing equation is that, as we saw in my derivation of the equation, and from the derivation we know that that term represents the net heat flow through the faces of an infinitesimal control volume. That is a vanishingly small control volume. And that term represents a heat generation within the control volume. And this is, both these terms are written per unit volume, and they have to add up to 0 for energy conservation. And they are defined, and this equation is defined from x equal to 0 to x equal to L. That's because our bar is of length L. And we need to put boundary conditions at the edges of the domain. So this is called the domain. When we go into ansys, we'll be specifying the domain by drawing the geometry, but this is what we're specifying when we draw the geometry for a lot of problems. The boundary conditions, first let's take a look at the left boundary condition. So we say that at the left boundary we know the temperature at some value T sub 0. So that's a value at that face. And at the right face we have the heat flow per unit area. That's a heat flow per unit area. So that's the boundary condition at the right face, and we know that value. And I should make it clear that this is heat flow per unit area. It's called heat flux. Earlier I used Q for heat flow, and now I'm using it for heat flux. My bad notation. So you have to be careful, whether what we're talking about is heat flow or it's a heat flow per unit area. In this case, it's a heat flow per unit area. And that's related to the temperature gradient at the right boundary through the Fourier's law. So essentially what we have here is the temperature gradient at this boundary. So we have the temperature here and we have the temperature gradient here. And the two major kinds of boundary conditions you have are the value or the gradient of the value. So this mimics both the major types of boundary conditions. Governing equation plus boundary conditions is called a boundary value problem. So let me write that down because it's a very important idea. So this is called a boundary value problem. It's governing equation or governing equations defined in a domain and boundary conditions defined at the edges of the domain. So to complete the boundary value specification, we need the governing equation, we need the domain, which we in the tool we'll be specifying in the geometry step, and then we need boundary conditions at the edges of the domain. The exact solution to this problem is straightforward. It's a simple linear differential equation, and I presume you've seen it while studying calculus. So let's think about how to solve this using the finite element method in order to understand the finite element method. That's what I'm going to talk about next.